Hi everyone. In this video, we're going to review polarity. So you might recall from general chemistry that electronegativity is a measure of the ability of an atom to attract electrons. So down below we have a pretty simple table of representative elements that we most commonly see. And listed beneath each element is an electronegativity value. So this is on a scale from 0 to 4, and you'll notice that fluorine has the highest electronegativity value, and electronegativity increases going left to right across a period, and it also increases going up a column or group. Now, hydrogen is kind of on its own. It, remember, is a non-metal, but it's typically listed in group 1. However, it does have some similar properties to the halogens as well, so it's kind of just sitting off on its own there. Now, you might also remember that if we're looking at a particular bond, we can figure out if that bond is polar or nonpolar, or even ionic, by taking the difference in electronegativity values. So for HF, for instance, hydrofluoric acid, we know that hydrogen has a value of 2.1 from the table below, and fluorine has a value of 4.0. So if we take the difference, we get a value of 1.9. Now, your textbook has a table showing electronegativity differences and what bonds those correspond to. So if you have an electronegativity difference between 0 and 0.4, we consider that bond to be nonpolar. So this would be something like carbon bonded to hydrogen. Or if you had just carbon bonded to carbon. Those differences are between 0 and 0.4. Now, a polar molecule, or a polar bond, I should say, will have an electronegativity difference between 0.5 and 1.7. And then any difference greater than that is considered ionic. So when we're looking up above at hydrofluoric acid, that has a difference of 1.9. So why is this still a polar covalent bond? Well, it has to do, again, with whether you have nonmetals or metals present. So remember, an ionic bond is between a metal and a nonmetal, and then a covalent or molecular bond is between two nonmetals. So there are some exceptions to the table below, because hydrofluoric acid does have a covalent bond, but its difference is greater than a polar covalent bond down below. However, we're still going to say that this is polar covalent because we have two nonmetals, hydrogen and fluorine. Now let's look at an ionic example. So let's say we have lithium fluoride. Okay, so let's find lithium. That has a value of 1. Fluorine again has a value of 4. So if we take that difference, we get 3. And that is much, much greater than 1.7, But additionally, um, we have a metal and a non-metal. Oops, my iPad is freaking out. There we go. So that should definitely be ionic. So again, the example of hydrofluoric acid is just to demonstrate that there are some exceptions to this table down below. So you do still have to think about whether you have an ionic bond or a covalent bond. Okay, now remember that you can also have partial charges in a molecule based on the polarity within that molecule. So looking at the hydrofluoric acid example again, we know that fluorine is more electronegative because it has a higher electronegativity value than hydrogen. So one way that we can indicate that fluorine attracts electrons more than hydrogen is to draw partial charge symbols. So they're little delta symbols. And we put a negative or a positive next to that delta symbol based on whether the atom is more electronegative, which would be negative, or less electronegative, which would be positive. You can also just draw an arrow with a positive sign on one end. So the arrow's showing the direction that electrons are moving in. So they would probably hang out with fluorine more. So let's do the same thing to the molecule below. We're going to look at each bond and figure out if it's non-polar covalent, polar covalent, or ionic. If any of the bonds are polar covalent, we're going to put a partial positive and partial negative sign along the bond. Okay, so let's start with carbon and hydrogen. So let's see if that is a nonpolar or polar or ionic bond. So let's go back to our table. So carbon has a value of 2.5, hydrogen has a value of 2.1. So if we take that difference, we get 0.4, which is, let's go back to our table, non-polar. And we can add the term covalent after that just to indicate that we have a covalent bond. Okay, so for each of the carbon-hydrogen bonds here, we don't have to assign partial charges, right? Because those are non-polar. So they're essentially sharing their electrons equally. Okay, what about carbon and oxygen? So let's go back. So again, carbon has a value of 2.5, oxygen has a value of 3.5. Okay, so if we take the difference, that is a difference of 1. And I'm taking the absolute difference here, so we're not going to have any negative signs there. Okay, so let's look back at our table and see. Okay, so 1 falls in this range, so it is polar covalent. Okay, so now we should assign partial charges. Okay, so which atom is more electronegative, oxygen or carbon? Oxygen. So oxygen should have a partial negative charge. Carbon will have a partial positive charge. Okay, now what about oxygen and hydrogen? So we already saw that oxygen has a value of 3.5 and hydrogen has a value of 2.1. So that difference is 1.4. Okay, so that would be polar covalent. Now we already put a partial negative charge on oxygen, and that is more electronegative than hydrogen. So then hydrogen would have a partial positive charge. So that oxygen is really drawing electrons towards itself, not only from carbon, but also from hydrogen. Now, if this has been a little confusing or you feel like you didn't quite follow the material, definitely try the Skill Builder 1.5 exercise. Even if this made complete sense, still try this Skill Builder exercise because it's really good practice. And this is on page 10 of your textbook. All right, so the last topic we're going to cover for this video is the net dipole moment for a molecule. All right, so we have CH2Cl2. So probably the first thing we want to do is draw the Lewis structure for this molecule. So which atom would go in the middle of this molecule? Carbon, right? It's by itself and it can make the most bonds. Okay, so now carbon has 4 valence electrons, and then we have 4 atoms that will surround that carbon. We have 2 hydrogens and 2 chlorines. All right, so let's just kind of put those around the molecule. It doesn't really matter where we put them, but also don't forget that chlorine has 7 valence electrons, so there will be 3 lone pairs on chlorine. Okay, so now we can make our bonds. So again, we could have just as easily put the hydrogens opposite each other and then the chlorines opposite each other. So these are both the same, even though they don't look the same. So remember that this molecule, or that carbon rather, has a steric number of 4. There are 4 things bonded to that carbon. And none of those bonded atoms are lone pairs, so this would be which geometry? Would this be linear, trigonal planar, trigonal, pyramidal? It would be tetrahedral. So in actuality, this molecule looks something like this. And we could have put the hydrogens in the plane instead of the chlorines, or we could have put one hydrogen in the plane and, one chlorine coming out of the plane of the paper. Wherever you put those atoms, carbon is going to have that tetrahedral configuration with its bonded atoms. And what is the bond angle? 109.5. Okay, so let's figure out whether we have any polarity in this molecule. So let's look at the carbon-chlorine bond, and then we'll also talk about the carbon-hydrogen bond. Now, the carbon-hydrogen bond we already went over, right? So actually, let's look back. So we already said that the carbon-hydrogen bond is non-polar covalent. Okay, so we'll just write that down. We already figured that out. So what about carbon and chlorine? Let's go to our electronegativity table. So again, carbon has a value of 2.5, chlorine has a value of 3. All right, so that difference would be 0.5, and that falls under the polar category. So this is polar covalent. And which atom was more electronegative? Chlorine. So chlorine will be partially negative, carbon will be partially positive. Okay, so what we can do is draw arrows showing where electrons are most attracted. Or you can draw partial negative signs as well. That's fine too. Now remember, the carbon-hydrogen bonds are non-polar, so we don't show any difference in the sharing of electrons there. So carbon and chlorine are sharing electrons unequally, whereas carbon and hydrogen are sharing them equally. Okay, so now let's get into the net dipole moment. So we can see that electrons are really attracted to those chlorines compared to carbon. And then we have the nonpolar carbon and hydrogen bonds. So overall, electrons are more attracted to the left-hand side of this molecule, which gives us a net dipole. So we have a net flow of electrons from the right-hand side of the molecule to the left-hand side. And it's kind of traveling right in between those two chlorines. Okay. So let's do some more examples of net dipole moments. So we'll figure out if BF3 and NH3 have net dipole moments. So if you want to try this on your own first, remember to draw the Lewis structure and then figure out the geometry. And then you can figure out if your individual bonds are polar or nonpolar. Okay, so again, the first thing we're going to do is draw the Lewis structure. And then we're going to draw the 3D structure. And then we're going to figure out the net dipole. So for BF3, which atom would go in the middle? Boron. Okay, so boron has how many valence electrons? 3. And conveniently, there are only 3 fluorines. How many valence electrons does a fluorine atom have? 7. So it has 3 lone pairs and 1 unpaired electron. So we're just going to draw all of our fluorines here. Okay, so now we can make our bonds. Great. Okay, so what is the steric number for boron in the middle? Or I guess another way of putting that is how many atoms is it bonded to? 3. And it doesn't have any lone pairs, because remember, in a steric number, we include both bonding atoms and lone pairs. Okay, so if the steric number of boron is 3, what is its hybridization? So is it sp, sp2, or sp3? sp2. And remember, you can kind of count the number of letters there. So we have 1 s and 2 p's. So it's 3 total. Okay, so I'm just going to draw a little arrow showing that this is sp2. Okay, so let's figure out the geometry of this molecule. What is the shape? Is it linear, trigonal planar, trigonal pyramidal, or pyramidal, however you want to pronounce it? Is it tetrahedral? It's trigonal planar, so that means that all of those fluorines will be equally spread out from each other. They want to get as far apart as possible. And what is the angle between two of those fluorines? 120 degrees. Awesome. Okay, so now let's figure out, do we have polar bonds? So let's go back to our electronegativity table. So boron has a value of 2. Fluorine has a value of 4. So what is the difference there? 2. So 4 minus 2 gives us 2. Okay, so initially we would think, oh, that's an ionic bond because that difference is greater than 1.7. However, is boron a metal or a nonmetal? It's a nonmetal, and fluorine is also a nonmetal, so it's actually polar covalent. So that's a little tricky. That's one of those other exceptions we talked about earlier. Okay, so fluorine is the most electronegative atom. So electrons are really traveling away from boron, and they're being owned more so by fluorine. So fluorine is kind of attracting the electrons towards itself more. Okay, so now let's figure out, does this have a net dipole? So are electrons being drawn in one particular direction over another? No, so this is the interesting thing with trigonal planar molecules. If all of the bonded atoms are the same, like in this situation, really those electrons are being pulled in equal or equally spaced directions. So it's kind of like a game of tug of war. So imagine you have 3 teams and 3 ropes that are all connected in the center, and people are pulling on those ropes. Now, if they're all pulling with the same force in equally spaced directions, the rope isn't going to go anywhere. And that's the case here. So we have equal forces that are all separated by 120 degrees. So there is no net dipole. Now what about NH3? So let's start by drawing the Lewis structure. So which atom should go in the middle? Nitrogen, because nitrogen has 5 valence electrons, and 3 of those electrons are unpaired, so it can make more bonds than hydrogen. Now, conveniently, we have 3 hydrogens and 3 unpaired electrons on nitrogen, so we can just draw those in here. Okay. So nitrogen has 3 bonded atoms and 1 lone pair. So what is the steric number on nitrogen? It's 4, because remember with steric numbers we include both bonded atoms and lone pairs. Okay, and what is the hybridization of nitrogen? Is it sp, sp2, sp3? sp3. So we have 1 s and 3 p's, so that's a total of 4. Okay, so now let's figure out the geometry of this molecule. Okay, so we have a few options. We have, let's see, tetrahedral, trigonal pyramidal, or bent. Which one is this molecule? Trigonal pyramidal, because we do have that lone pair. So this molecule will look more like this, where we have sort of a pyramid shape on the bottom, and then the lone pair is by itself on the top. And that lone pair is really pushing those hydrogens a little closer together than they would be in a tetrahedral molecule. Lone pairs need a lot of space to themselves. Okay, so now let's figure out where electrons are traveling, if they're traveling anywhere. So let's go back to our electronegativity table. So we have hydrogen again, which is 2.1, and nitrogen, which has a value of 3. So what is the difference between 3 and 2.1? 0.9. So that falls in the polar category. Okay, now which atom was more electronegative, hydrogen or nitrogen? Nitrogen. So electrons are traveling away from hydrogen and more towards nitrogen. All right, so does this have a net dipole? Yes, it does. So the electrons are traveling up towards nitrogen, and they're all kind of at an angle here with the bonding. So electrons are overall moving up. So it's kind of like maybe little people climbing up a pyramid. If they're all climbing upwards, then they're all going in the same direction, and that means we have a net dipole in the towards nitrogen. Okay, so then number 3, yes, we do have a dipole. Oh, I went ahead of myself here. Okay, so if you do want more practice with this, I recommend trying the Skill Builder 1.9 exercise on page 31. All right, so that brings us to the problem of the day 2. This is on Canvas under modules, or you can use the link on the homepage calendar. And for this pod, There is a hint. You might want to look up the definition of a Lewis acid. Also, what is the hybridization of boron? And it might help to draw the hybridized orbital diagram. Oh, and I forgot to write the due date for Pod 2. That is Sunday, September 27th at 11:59 p.m. So it's the same as Pod 1. Okay, now in the next video, we're going to talk more about intermolecular forces. So I will see you there.